Okay, so today I'll be going over some existing and ongoing work with my supervisor, Elena Casares, and our collaborators, Arnab and Ayan, on black hole interiors through the perspective of holographic RG flow. So first I'll give an overview of what we're doing, then I'll talk about some of the machinery that we use. Then I'll go into the paper that we have, and then I'll conclude by talking about some work in progress. Okay, so there's this nice story in ADS-CFT about how data about the interior of a black hole, and in particular, data about its singularity, is encoded in the boundary data, so things like correlators, through analytic continuation. And there's an old paper from 2003 that did this with 2-point correlators and signals of the singularity in the bulk. And there's also a more recent paper in which about how 1-point functions encode the proper time from the horizon to the singularity. So what we're going to do is we're going to consider, just for a moment, an RG flow that goes from some UV fixed point to some IR fixed point. And then once we reach the IR, we'll analytically continue the energy to a trans IR flow. And credit goes to Sean Hartnell for that name. And what I want to argue now is that that's very natural to think about in holographic RG flow. So as a reminder, holographic RG flow is just a program by which I think about the bulk extra dimension in ADS-CFT as being some energy scale for some RG flow from the UV, which lives on the boundary, to the IR sitting somewhere in the bulk. And this RG flow is triggered by some operator that's dual to some bulk field. Now, one can ask about black holes because if you think about the radial coordinate of a black hole, it's space-like in the exterior, but it becomes time-like in the interior. So we essentially reach the IR when we're at the horizon, meaning that the UV to IR part of a flow will only see the exterior. So the interior is a trans-IR flow through the perspective of holographic RG flow. And so holographic RG flow gives us such flows because of just the existence of black holes. So our goal today is going to be to understand the physics of such trans-IR flows, with the hope that that could teach us more about black hole interiors. Now, so far, we have some work that's actually about page curves. And what we did here was we considered a holographic RG flow. We added a Karch-Randall brain to it in order to get this doubly holographic setup, which I'll talk more about later. And originally, we were motivated to ask about what happened, what deforming the bath of such a setup might do to page curves and islands and all that stuff. And what we ultimately found in our simple setup was that the page time was essentially pushed up for flows that ran faster from the UV to the IR. So flows that were more deformed. But the objectives of our work that's ongoing is to kind of understand these trans-IR flows a little more generally, and in particular, to understand how exactly the interior is encoded through the RG flow. So a probe of RG flow that you could think about for holographic RG flow anyway, is a holographic A function, similar to such functions that have been considered in the past. So we've come up with essentially a glorified guess that seems to behave the way we want. It seems to be monotonic, and it seems to be stationary at the UV and the IR. But part of our work now is trying to get a better justification for our guess and also to understand what it might mean physically. Okay, so the particular class of flows we'll think about as just a simple example is a free scalar field in the bulk coupled to Einstein gravity. So if you want relevant deformations of the boundary, you need to consider scalar fields which have negative mass squared, just by the usual mass dimension relation of ADS-CFT. And we'll particularly focus on this Schwarzschild-like ansatz that's radial. It looks a lot like Schwarzschild, except there's a warp factor in GTT. So we have these two radial functions, f and chi. We'll also consider our radial field to be, or our scalar field to be radial. And upon using this ansatz, your equations of motion will become this a highly nonlinear set of ODEs, which you can't possibly hope to solve analytically. So we'll do so numerically by some shooting method. And when we solve for a particular flow, each such flow will be labeled by some dimensionless parameter. That's just the source of the scalar field divided by the temperature of the black hole raised to some power. Now, what you can say analytically is you can actually look at the near singularity behavior of the metric and of the scalar field as well. The scalar field will have this logarithmic divergence at the singularity, but the metric will actually have this, will be controlled by these PT and PX scaling exponents. And what you can find classically is that the PT, PX, and P phi, those satisfy the constraints in 2.8. So this hyperplane constraint and the sphere constraint. So these are Kasner exponents. These are the Kasner constraints. So the PT, PX, and P phi are Kasner exponents. So our near singularity geometry is that of a Kasner universe. And so these flows have in the literature been called Kasner flows. And I refer you to this paper, which served as a major source of inspiration for us. Okay, so let's talk about our existing work. So I'm going to start by just reviewing doubly holographic models real quick. So when we have our theory of Einstein gravity, we can add an end of the world Randall-Sundrum brane to the theory as well. And it's going to be characterized by some tension. Now, if I take the tension to be subcritical, then I get something called a Karch-Randall brane. The induced geometry on such a brane will asymptotically be ADS-D. So I have just an ADS-D geometry on the brane. And I also get this double holography. So I have my bulk theory, that is this D plus one dimensional Einstein theory with my end of the world brane. But I can dimensionally reduce the theory to one that's just localized on the brane, shown in red, and this conformal boundary, or back, as I call it, in black. So I have this brane plus bath picture where there's just CFT matter living everywhere on the brane and on the bath with a transparent boundary between the two. And I also get gravity, which localizes to the brane. I can also further dimensionally reduce this to just a QFT that has a codimension 1 defect, that is this red dot here. So that's going to be a BCFT, and that the equivalence between that and the bulk perspective is the ADS-BCFT correspondence. And one thing that's nice about double holography is that I can study islands if my brane plus bath theory is greater than 2 dimensions as follows. So normally, if I want to think about the island story, I want to think about quantum extremal surfaces. So here I'd want to think about quantum extremal surfaces of the brane and bath theory. Those are encoded by classical surfaces in the bulk. So I get this to leading order in 1 over G Newton, this island rule that says if I want to compute the entanglement entropy of some interval in the bath, I can do so in the bulk theory by considering classical extremal surfaces. Now, I would actually consider surfaces which aren't just homologous to R, but are homologous to R union some intervals on the brane, and I would minimize over all of those surfaces, minimizing over the interval on the brane as well. And that includes possibly the interval being the empty set. So that will give me not just the entanglement entropy, but that'll also give me the island for a particular time. Now I'm going to consider an eternal setup here. So on the brane, I just have this eternal two-sided black hole, and I'm going to collect radiation on the left and on the right. From the bulk perspective, I get a phase transition of entanglement surfaces from one corresponding to no island to one corresponding to an island that extends outside of the interior. Now, if I add a scalar field to the bulk perspective, I'll get classical back reaction that should inform the numerical details of this curve. And that's what we saw. So this was just the example of D equals 3 with a 2-dimensional operator, and we kept the radiation consistent. And what we saw was that if we had no deformation, we got one page curve, this thing in this dashed line, which the page curve, of course, is the increasing part, and then the constant part after that. But then for another choice of deformation, say 35 for my parameter, I get a different page curve with a higher page time and a larger initial gap. And I can do this for more parameters. And this monotonic behavior was something that we just saw in our numerics for various choices of D and delta. So we're going to just take this one-to-one monotonic increasing of the page time as a feature here. So there's a way to look at this through the lens of RG flow. So if I fix D and delta, then every choice of deformation parameter will tell me a particular flow, including what the trans IR looks like. But if I also fix the radiation, then I'll get a particular page curve, which tells me which flow, which deformation parameter I'm on. And that's because of the one-to-one behavior of the numerics. Now, one can ask, what does it mean to increase the deformation parameter? Essentially, it means that, so you have a more deformed flow. Essentially, you would have, for a probe like the page time, which seems to be telling us something about the entire flow, it would have stronger, basically we would have stronger effects, stronger contributions from whatever's going on in the IR or trans IR. That's kind of a loose idea of what might be happening. So in some sense, like what we're trying to claim is that when the IR effects are more important, the page time should go up. And we're inspired by this BCFT result that was obtained in a similar setup, but on the BCFT side, where the authors found that page time, when is 1 over the number of degrees of freedom of the BCFT state. Okay, so that's what we had. And what we're working on is we're trying to understand these trans IR flows a little more generally, apart from just thinking about page curves. So I'm going to briefly talk about this, but consider the following blackened domain wall. So we have our factor of F there. If I just set F to be 1, then I get a well-known domain wall with flat slicing, for which the A function has been written down long ago and has been studied a lot. And if you have the null energy condition for whatever matter lives in your bulk, then this A function is known to be monotonic in any dimension D. But we care about black holes. So we're going to consider the case where F has a simple root at rho equals 0. And in doing so, we propose the following guess, where we have a factor of F in there. We're still trying to think more about why this might be a reasonable thing to guess, apart from just writing it down. But you can do a few sanity checks to see, does it behave how we want it to behave? The first one is this stationary for ADS Schwarzschild? So if I just consider the situation where there's no deformation, I'm just stuck at the UV, it's a stationary. And in fact, it is. You can plug in these functions, you can see it is. And in fact, it reproduces the same A that you get for just empty ADS. We can also write it in terms of the Schwarzschild-like coordinates from before with the F and the chi. And we get this expression 4.5. We would do this because it turns out it's easier to prove monotonicity in these coordinates. I'm not going to be able to talk about that today in detail, but I'll just show you that monotonicity means showing that in the exterior, A increases with rho, but in the interior, A actually decreases with kappa, which is the imaginary part of rho in the interior. But we can actually plot that function for Käsner flows because we have the flows numerically. So for D equals 3 and delta equals 2, this is what we got for the A function for a variety of different deformations. So for no deformation, it's just constant, expected. But for a bunch of other deformations, we saw this decreasing with respect to R. The horizon here is the dashed line. So to the left of the horizon, we have the UV to the IR, and then to the right, we have the trans IR. Then we also plotted its derivative. So on the left, we had that dA d rho, which needed to be positive, which it certainly is. On the right, we have that dA d kappa, which needed to be negative. It certainly is. Furthermore, I hit 0 at the IR. So A is in fact stationary at the IR, which is, again, what we want. So monotonicity does look like it's certainly obeyed numerically for these Käsner flows. Okay, so just to wrap up, essentially the story that we have so far is that trans IR flows are a very natural thing to think about in holographic RG because they're just black hole interiors. And we've tried to think about how page time might be a probe of such flows, but we also want to study this monotonic A function that we came up with, which seems to work behind the horizon. And we've used Kasner flows as being our test case here because it's the numerics are straightforward. But what we still need to do is we want to further justify the guess that we wrote down. We also want to understand what exactly this guess is supposed to represent physically, because there's a nice story about how the A function in holographic RG flow typically means is like some coefficient of entanglement entropy. But also kind of a more broad question might be, what exactly are we doing to a state when we subject it to a trans IR flow? Okay, that's all I've got. Thank you.
Oh, the perfect timing.
Ooh, nice.
Questions?
So in these trans IR, you know, like what exactly is the relation between the things that you do and is there a precise connection? Or?
Yeah, it's we're still trying to think about it. Maybe one thing I can say, so through the lens of holographic RG flow, if different theories or different states along the flow live on radial slices, the scaling in the trans IR, like the radial coordinate is time-like, but that would mean that the slices themselves are Euclidean. So I don't know if there's like a Lorentzian way of looking at it, but
Sorry,
maybe.
You have a Lorentzian ADS boundary, or you could.
So let me go back to the metric. Maybe okay. So this is the metric we have. When we're in the exterior of the black hole, it's all very familiar. We have just like Lorentzian, we take constant row slices. Those are going to be Lorentzian. So the slicing is Lorentzian when we're in the exterior. But when we're in the interior, the signatures will change. So the signature of T will now become positive. So constant row slices will actually be Euclidean. But that's basic. So what we think is that moving along the flow in the interior is it might be some sort of Euclidean evolution. But we're still trying to think more about what we might be able to ask concretely to clarify that story.
Maybe part of the answer to my question is your equation 4.2. It looks like a quantitative relationship between A of rho, which is something that I think you might be computing on the CFD side, and capital A of rho, which is the scale factor, the metric.
Mm-hmm.
Can you compute little a of rho from the CFD?
Yeah, okay, yeah. So this little a of rho, so first of all, this little a of rho that's written here, that's for flows that don't have any sort of changing in the signature. And there's a story about how you can realize this A in terms of for even D in terms of the trace anomaly on the CFT side. In more recent memory, there's a story about how for any dimension D, you can realize O on the A on the CFT side by computing entanglement entropy of like a subregion of a vacuum state. So you can compute this on the CFT side. And one thing we really do want to be able to do.
But this is an A that depends on the length scale, not the CFTs, not the UV CFT.
Not just the UV CFT. Yeah, I guess it's really more appropriate to say, like, from the perspective of just a QFT, this A does have meaning as entanglement entropy or as a coefficient of entanglement entropy.
Okay, and that meaning goes over to this.
That we're not sure about. That's what we're still, we definitely need to answer that question though for this to really be fleshed out, but we're not sure yet.
Thanks.
In some of these early flows, there's a singularity that forms in the IR. And well, there's some Gobser criterion to tell you if it's good or bad, but say if it's good, you can hide it a little bit behind the horizon, but behind the horizon, there's a singularity. Does that affect anything that you're saying here?
So one thing we do know about the singularity, at least, so all we really know about the singularity through this function is that, so we have this monotonic decreasing, that's not affected by the singularity, but it does seem like A goes to 0 there.
Exactly. That's the sign of the singularity that the theory gaps out.
Okay, yeah, so that we did see that, so I didn't have time to get into it. But we do actually, at least for Kasner flows, we do actually see that just from the structure of the Kasner solutions near the singularity.
Okay, I suggest we find Sanjit again.
Okay.